we're talking about the radius of an atom, what is the trend, the trend on the periodic table, or is there a trend? You know what I'm talking about? How big it is. You know, is there a trend on the periodic table that we talked about?
Was it from left to right is larger to smaller, and from top to bottom as well?
You're saying from left to right, it gets bigger or gets smaller?
It gets
Bigger.
Yeah, rusty. I think it gets smaller.
It gets
Okay.
smaller the farther you go left, right?
The correct answer, it gets smaller.
Nice.
Smaller. As we go from left to right, it gets smaller because there are more positive charges in the middle, and they're going to be pulling those electrons closer to it. Okay, now what about top to bottom? From top to bottom, bigger or smaller?
Smaller as well?
Now think about it. Now, this case, what you're doing is kind of like the Russian dolls. So each level, put another one on there, you're putting another one on there, you're putting another one on there, you're putting another one on there. So is it going to be bigger or smaller?
Bigger.
Bigger.
Okay. It's not working for me today. So it gets bigger as we go from top to bottom. Okay. Now, if we're talking about the electron affinity, you guys remember what electron affinity is?
No.
Oh, can you repeat it?
Electron affinity. Do you remember what electron affinity? I'm gonna spell it for you. Sometimes just seeing a word, it helps me out. Have you heard of the word affinity before? If you have an affinity for something?
Yeah, it means you're like really good at it.
It's how well you get along with something, or
No, not get along.
Affinity is like you're really an expert in it. Like
Not quite. It's not necessarily an expert, but maybe a desire.
oh, a desire? Oh, okay.
Yes. Or a want, you know, really, really, really want, you know. So affinity is kind of like a desire, right? So electron affinity is like the desire of an electron. So who's going to want to get an electron the most? Who do you think is going to be like, damn, I want that electron so bad. Give it to me.
Non-metals.
Non-metals, yes. Which one? Which one is going to have the highest electron affinity? Who's going to be like, yes. I talk about this guy all the time because I say he's a bully.
Was it a fluorine?
Fluorine. So fluorine has the highest electron affinity. Okay, so if fluorine has the highest electron affinity, which would we expect electron affinity to go from low to high? Which way would we go, left to right or right to left?
Can you ask that again, please?
So if I'm trying to figure out the trend of electron affinity, would I want it to go from left to right or right to left?
Left to right.
From left to right. It's going to increase from left to right. So it increases from left to right. And then what about from top to bottom?
Bigger.
Decreases.
It's going to decrease from top to bottom, or we could say it increases from bottom to top. Right? Meaning, again, if fluorine is the most electronegative, the one that has the most electron affinity, then the guys below it are going to be less than, right? That kind of makes sense. So then you'd assume that this guy, if this is the greatest, then these other guys are going to be a little bit lower. They're still going to be pretty good overall because they have a strong desire to get an electron. Does that make sense?
Yes.
yes.
Yeah.
Angie? You going to do my hair next?
I'm getting there.
You're going to get mine next? Is that what you're telling me? Okay. So, what about ionization energy?
Dr. Henry, what was electron affinity again? It's the
It's like
lose-
the desire
gain
to
an
have an
electron?
electron or to get an electron.
Oh, so not to lose anything, right?
Not to lose anything. No, it's
Okay.
to get,
Okay.
to acquire. Okay. What is ionization energy?
Um,
Let me give you a hint. In this case, it is to kind of get rid of something. But what are you going to get rid of to become an ion?
Electrons.
Electrons. Okay. So ionization energy is the energy required to get rid of an electron, right? Because there's like even if you're losing an electron, it takes a little bit of energy to do it, right? It's like nothing is totally free. You know what I'm saying? You know how like TurboTax says free, and then you have to go and pay for it at the end? It's free for you to use their program until you're ready to submit it, you know? And you have to pay. So not many of you guys do your taxes. I forget you're in high school. I mean, not high school, you're in college. You're in the first couple of years of college.
Yeah, TurboTax pulled that on me this year.
Okay, ionization energy. So what is the term for ionization energy? So it's the energy to lose an electron. Who's going to have the lowest ionization energy? Who's going to have the highest ionization?
The highest will be metals.
Are you sure? So remember, it's the energy to lose an electron, right? So the more it takes, the harder it is to lose. The higher the energy, the harder it is to lose an electron.
So would it be on the farthest right of the periodic table? Like farthest?
Okay. So you're saying, is it going to increase from left to right? So if we go from left to right, is it increase or decrease?
I thought we said it was increasing, right? Or no?
That is right.
Yeah,
No,
yeah.
you're right. It is increasing.
Okay. So then it would be farthest right would take the most energy. So like noble gases?
That's right. The noble gases would take a lot more energy because they don't want to lose an electron, right? So they're going to put up a fight. So if you kind of look at it, it's like it's the energy to pluck an electron, right? So who's going to be easier to pluck an electron from? A noble gas or a metal?
Is it less hard to get an electron from them because they've already reached like a homeostasis, like, you know, balance or whatever?
Did you say it's less harder or harder?
It's harder, right?
It's harder, yeah. It's
Okay.
going to be harder because they're stable, right?
They're balanced. Yeah, right.
Yeah,
So
they're already balanced. Their octet is completely full, right? Because
Yeah.
their octet is completely full, they're not going to lose an electron. They'll fight you for it, right? They're like, nope, you're not taking my electron. This is going to take some effort. You got to be really strong. You got to be like fluorine to try to take my electron, you know? So there's going to be a strength associated with it. So these guys are going to have the greatest and increase, highest, and then these guys are going to be the lowest. So is it also going to increase from top to bottom or decrease from top to bottom?
it would increase, wouldn't it?
Would it? So think about it. Now it's pulling an electron, right? Now, okay, we'll put it like this. So if you have two kids, right? What is the probability of somebody coming and stealing your kid?
Very low.
Very low. If you have 100 kids, what is the probability of somebody stealing your kid?
Still very low for me.
For you, are you sure? If you had 100 kids, I'm sure you said, no, you can take them. Just don't bring them back, right?
Yeah, I hear what you're saying though.
Okay, so the more electrons you have, the easier it's going to be to sit there and take it away.
Okay,
Right?
I got it.
So in this context, who's going to be have the lowest ionization energy?
That would be the bottom left of the chart because it's the farthest left and it has the most electrons, right?
So that is who?
Francium?
Francium. Okay, so we know that ionization energy, it will also increase as we go from bottom to top, or we could say decrease from top to bottom, right? Okay, how you feeling so far? Is it starting to come back slowly?
Yeah, it's making sense.
It's coming back
Sal?
little by little.
Little by little? Angie?
Yes, we're getting there.
Daisy?
Yes.
Yes. Okay. Okay. So I have one more. Metallic characteristics. Okay. So who's gonna is metallic characteristics gonna increase going from left to right or right to left?
Say it one more time.
Metallic characteristics.
Well, all the non-metals are on the far right, so it probably goes right to left as it increases right to left.
That is correct.
From right to left, more metal-like.
That's right.
Yo, what's happening? Am I actually learning chemistry right now?
Oh, yeah, you guys are scaring me. Wait a minute. Maybe you guys need to take a spring break a little more often.
Or we just want to be Kalinga.
You just want to be Kalinga? See, that's what I have to do. So now I have to talk to Kalinga and say, you know what? They've been talking mess about you guys. Okay, so what about from top to bottom or from bottom to top? Is it going to increase from top to bottom or increase from bottom to top?
Top to bottom.
Bigger.
You said,
Oh, the metallic.
yeah, the metallic. That is correct. From top to bottom. So francium would be more metal-like than any of the others. Okay. Simple?
Yeah.
Okay, good.
Increase. Okay.
Okay, good. So now we can start talking about some other things, right? So let's get started on, oh, I should ask, are there any questions before we get into the nitty gritty?
So far, none.
No questions? Okay, good. I'm not used to that either. Usually there's always one about, so what is due this week?
Actually, I have a question, Dr. Henry.
Okay.
It's well, maybe we'll get to it, but how do we know which atom would be the center of the Lewis dot structure?
Ooh, that's a good question. So there's a couple ways to sit there and figure that out. The most common way is by looking at the electronegativity. We're going to talk about the electronegativity today, hopefully. If not, we'll definitely be talking about it on Wednesday.
Okay.
So let me show you the quick and simple way, quick and dirty, but there are some stipulations on it that'll kind of throw you off. Okay, quick and dirty is the guy that's typically closest to the noble gases. They're not going to want to be in the middle, right? They're strong, so they're going to be on the outside. They want to make sure that they get their octet before anyone else's, and so they're not catering to it. Carbon's a whore. Carbon likes to have at least 4 attachments if it can, so 4 bonds all together. And so carbon likes to be in the middle, right? Okay, so, and then these guys don't like to be in the middle. And then as you move away from the noble gases, you get weaker. Does that make sense? So you often will get put in the middle. So how many of you guys have siblings?
I do.
You got 1 or 2?
2.
You have 2? Okay, so did you guys ever go on road trips?
Yes.
How did you guys get to choose who sat in the middle?
Oh.
The young.
Wait, we reviewed this last week, right? With
Yes, we did.
Kalinga. Little one sits in the center because they're the smallest.
Yeah, so the weakest one, right? Usually the smallest one is the weakest one,
Dang.
right?
Not here.
So, what was that?
Not here.
Not here.
Tell us from my sisters.
Right, because I was strong for a while, right? And when my sisters were little, I was the strongest one. I was like, yeah, I'm not getting in the middle, and I pushed them in the middle, right? As soon as you know that they jump in, I got the seat, and I just push them over. Nope, you're going in the middle, right?
Mhm.
So I push them in the middle all the time. That's the same
Mhm.
way with the atoms. The weakest one is going to sit in the middle. So the guy who has the weakest electronegativity is the desire to get an electron, associated with it. I'm pulling the electrons towards me. They're going to be in the middle. Weakest guy goes in the middle. Okay. Carbon likes to be in the middle. It likes to be submissive to everyone else. It's like, hey, let me make you happy, right? It tries to make everybody else happy. So everyone else is going to try to get their octet filled before carbon. So carbon is always going to try to cater to everyone else. Okay. Okay. Questions, concerns, catch.
So you're saying carbon doesn't mind to be in the middle?
Carbon is like, yeah, I like being in the middle. Yeah, for the most part,
Okay.
it's gonna. If you have an option, and carbon is one of those options, carbon is going to be the one that's going to be in the middle.
Okay. Thank
Okay.
you.
Majority of the time, of course, there's always going to be an exception to things, but majority of the time it will be. So does that help? Is that Pedro?
Yes. Yeah.
Okay.
That sort of helps, I guess. Yeah.
That sort of helps. Don't worry about it. We'll clarify. We'll have numbers and everything like that to make it a little more permanent, and then it'll be like, okay, I see. But there's just the general trend, that you can also take a look at the periodic table, and it kind of helps you out a little.
Okay.
Okay, so let's get started talking about chemical bonds. I can't remember all the stuff we went over. It's all a haze. And then when I say it once, everything sits in my head. I'm like, we already talked about that.
Did we go over the Rutherford experiment or whatever? Because that's on the test, and I was like, I had never heard of it before.
We did talk about the Rutherford experiment.
We did.
The whole thing with the foil.
Yeah, the gold foil, right? I mean,
Yep.
I read about it on my own, but I just didn't remember us talking about it. And then
Yeah.
they
Yeah, we talked about that was the first week of class.
Oh, that was first. Okay, that's why I didn't remember it, man. I got 1 week attention span. You know what I mean?
Okay. Well, you're in chemistry now. Everything that's from the very beginning to the very end, they all kind of blend together. It's building on each other. Okay, so let's see how much you guys remember as well. So we've talked about ions before, right? What is a cation?
It's a positive charge ion.
It's a positive charge ion.
It loses electrons.
Okay. And an anion?
Negatively charged and formed when an atom gains one or more electrons.
Okay, that's good. You guys can read the board. I'm proud of you.
I thought it was Cation and Anion.
Okay. Oh man. Thank you, Veronica. I needed that.
No problem.
Okay, so now you know it's not Cation and Asian. Okay, so
Anion.
Anion. Okay, Anion. Okay. Okay, so cation, positive, right? Good way of remembering it. I know, bad joke. Okay. Okay, so cation and anion, right? So we know about a cation and an anion. We also know how they're forming, right? You guys remember how they're forming? Who's going to form cations? Pull up my periodic table.
Metals.
Metals, that's right. Metals are going to want to form cations, right? Because in most cases, they're going to want to try to get rid of, those electrons, right? Where, who's going to form anions?
Non-metals.
Non-metals, because they're going to want to get electrons, okay? So if we take a look at, let's say, sodium. So we have sodium here, right? So why does sodium want to get rid of an electron?
It's easier and to get closer to that noble gas status.
Because it wants to be like a noble gas. Because we know that being like a noble gas gives us stability, right? So it wants to be like a noble gas. And the way that it does that is by getting rid of an electron, right? Because when we're thinking about things, right, it's about whether we're going to be either give away electrons, give, or we're going to take electrons, take, right? And so those are examples of ions, or we can share, right? And we'll be talking about that sharing here in a minute, okay? So when things are being given and taken, right? When, in the case of sodium, you said wants to give up an electron so that it can be like who? Which noble gas?
Like
Neon.
On.
Neon. So in that context, it would be just like neon. So if we looked at sodium and we looked at the electron configuration of sodium, what is the electron configuration of sodium? But just sodium, not sodium plus.
Shoot.
could be neon 3s1.
Okay, it would be neon. (3s1). Okay, so if we lost one electron, what would it be?
Just neon.
It would be just neon. That means that it would be what we call isoelectronic to neon, meaning that it has the same number of electrons as neon. Okay, so sodium plus is going to lose that one electron. Okay, and so then it's going to be just like that noble gas. Now let's say we have nitrogen. You guys see nitrogen?
Yes.
Okay, what is the electron configuration for nitrogen?
Would it be helium and then 2s2?
Helium,
2p and then 2s2.
2p what?
2p3.
2p3. Okay. Okay, and so what is helium? I mean, what is helium? What is nitrogen going to want to do?
Add 3 electrons.
It's going to want to add 3 electrons, and if it does that, it's going to form an ion that's 3 minus because it's added 3 electrons. And then what is going to be its electron configuration?
Would be helium 2s2 2p3 or can it be 2p6?
2p6, that's right. Because we're adding 3 additional electrons. Okay, or we could have just written it as
Neon.
neon, because that would be the same electron configuration for neon. Simple?
Yes.
Okay,
Kind of.
so these guys, because they all have the same number of electrons, right? These guys as neon, these guys are called, as I said, isoelectronic. Okay? You with me so far? Okay, so let me take you to another level now. Now, this doesn't just happen in a box, right? So sodium doesn't just go ahead and leave its electron. It tries. Don't worry about it. We'll talk about that a little bit later too. It doesn't just drop its electron and say, okay, I'm done. You know, usually there has to be some type of exchange, right? And part of that exchange, it involves ionization, right? So you need to kind of get over the hump. So you need something to kind of help it get over that hump. And one of those things that are helping it get over that hump is the presence of another something that wants to gain electrons, okay? And so let's talk about, say, sodium and chloride. So if I had sodium and chloride together, right? Sodium wants to do what?
Give up an electron. So would it be?
It wants to give up an electron. So it wants to become Na+. And chlorine wants to do what? It actually wants to gain an electron. So it becomes Cl-. And actually we know that we're talking about chlorine gas with Cl2. So we'd want to get Cl minus, okay? Now, what happens when you have one that's giving up and one that's wanting to take? They're going to make a chain exchange with each other. Sodium is going to say, okay, I give it up. You give me a little more energy, and then you can take it, right? And so he's going to give up his electron. Sodium's going to give up his electron, and chlorine's going to take it. Okay? Now you have something that's positive, and you have something that's negative. What happens when you put positive and negative?
They attract each other.
They attract each other, right? So because they attract each other, we get a compound that forms that balance each other out, called sodium chloride, which we know as salt, right? Yeah?
Yes.
Yeah.
Okay. Okay, now the key is when we're talking about this, this is called an ionic bond, right? They're bonding together using ionic charges. They form ions and they come together. They have to balance each other out completely. They have to have a total charge of 0 for them to be a complete ionic compound. Does that make sense?
Yes.
Okay, so, or ionic bond, okay? So the goal is to try to sit there and balance them out. We have to find ways to balance it out. This was a positive charge, this was a negative charge. One positive, one negative. Put those together, doesn't that equal 0?
Yes.
Yes.
Okay, good. Now that we've established that, let's see how good your math is. Okay, let's assume that we have O2 minus forming, and we have potassium plus. Okay, how many potassiums am I going to need to balance out that one?
You will need 2.
I will need 2. So, and then that's going to give me okay. And you notice I don't put a charge on that compound because it's completely balanced. You guys see that?
Yes.
Yes.
Okay. Make it one more time. What if I have manganese and phosphorus? What's going to happen?
Wait, you said manganese, but you put magnesium. Did you?
Sorry, my bad. Magnesium.
Okay.
Yes, I meant magnesium. I'm thinking manganese or something. We'll get to that in a minute.
Phosphorus would be 3 minus, but magnesium looks like it would be 2 plus.
Okay, so phosphorus is going to be 3 minus. That's right. And magnesium is going to be 2 plus. Is that going to balance each other out?
No.
No. So what do I need to do? How many of them am I going to need to balance those charges?
One more magnesium.
I'm going to need, you said 1 more magnesium?
No, we need 3 plus magnesium.
So how can we get 3 plus magnesium?
Or you can get 3 magnesium and then 2 phosphorus. That would be balance it out.
Okay, so if we have 3 magnesium, 2 plus, and then 2 phosphorus, 3 minus, that's going to balance out. That's going to be a -6. This is going to be a +6. So
This is like a whole different way of balancing equations.
well, it's not balancing equations. Now you're balancing the compounds. Okay, so in the chat, I believe, wait, you see. There was a couple of questions.
I have a question, Dr. Henry. What is this called so I can watch some more videos later? Because I'm understanding it, but I want to research it. Is there like a name for doing this?
ionic bonds.
Okay, thank you.
Okay. Okay, so let's talk about this. Okay, so the first thing was, one of the first questions is, how do I determine the charges? Well, we know that group one metals is one away from being a noble gas. It loses one electron, it becomes positive, right? Because an electron has a negative charge associated. Are you there, Andrea? Andrea? Okay, good. Okay, so I'll repeat that. So we want to be like a noble gas. So sodium wants to be like a noble gas. It needs to lose one electron. Electrons have a negative charge associated with it. So if we lose one of them, that makes that compound, or that element positive, because we lost one. It makes it an ion, a positive ion. So sodium would be plus. Magnesium is 2 away from being a noble gas. It needs to lose 2 electrons. So if I lose 2 electrons, then magnesium becomes what? What's going to be the charge associated with magnesium?
2 plus.
2 plus, okay? Aluminum is 3 away from being a noble gas. So if it loses 3 electrons, what's going to be the charge on aluminum?
3 plus.
Okay. Okay, so you guys kind of get that. You see how that works?
Yes, plus is minus and minus is plus.
Okay, so phosphorus, and you always want to go the easiest way, right? You always want to, because it's just like us. We're kind of lazy, right? If somebody tells you, look where phosphorus is at. If someone told you they pay you $500 from mowing 3 lawns, or $500 from mowing 1, 2, 3, 4, 5 lawns, what would you do? Would you mow 3 lawns, or would you mow 5 lawns?
3 lawns.
Right? Why would you do that?
Same amount of money.
Same amount of money, and it's easier, right?
Correct.
Ah, that is correct, Adam. That is very correct. So Adam asked, he says, so does that mean silicon can be either negative or positive? Yeah, silicon and carbon, they're kind of in the middle, right? So technically they can be negative and positive. So it really just depends on who they're pairing up with and what they're trying to do, right? So if you have, in most cases, carbon with the metal, then carbon is going to be negative. Okay?
But then it has to move farther.
No,
Because
where carbon is located.
Right, but it would have to.
1, 2, 3, 4.
Right, but if you go
Or
back.
1,
I got you.
2, 3, 4.
My bad, I'm
Or
done.
either way.
That's why I'm number 6 out of top 6.
You know, you guys keep me on my toes. Okay, and silicon is going to be exactly the same way. It's 4 either way. So, okay, are you guys ready for another one?
Yes.
Okay, so let's do aluminum and let's do aluminum and sulfur. No, it wouldn't be either. It wouldn't be and. It's one or the other, right? For boron. Boron, what is easier? Brianna, is it easier to lose 3 or is it easier to gain 5? Which one would be easier? Hold on. Now I want you to think about it. So you have the option. You could go this way. You can lose 3, 1, 2, 3, or you can gain 1, 2, 3, 4, 5. And it takes roughly about the same amount of energy to lose an electron, to gain an electron. Which one would be easier to do? Put it like this, okay? There's a store 5 blocks ahead of you, and there's a store 3 blocks behind you. Which one would you go to? They sell the same stuff.
You said 3 ahead and 3 behind?
No, I have 5 blocks ahead of you and 3 blocks behind you.
3 behind.
Why?
It's closer.
It's closer, right? Does that make sense, Brianna?
Less effort.
Okay. Okay. So what would be the charge on aluminum? Edgar, since you've already given me the answer.
It would be 3 plus.
And then sulfur?
2 minus.
So how many sulfurs will I need to balance out my aluminums?
3 sulfurs to 2 aluminums.
Okay, so then we'll end up with Al2 S3. You guys see that? Anybody not see it? Okay, there's a new message.
I'm still trying to figure out how we get -2 for sulfur.
Yeah.
Here's
I mean,
sulfur. How can it become a noble gas?
Oh, 2 steps behind.
Oh, okay, okay.
Okay, so that means 1, 2. That means it needs to gain 2 electrons, right?
Okay, yeah, that makes sense.
Okay, so Catherine, what is it that you don't get? You gotta help me. If I can't help you if you can't help me. Okay. Okay, so let's do one more for good measure. Okay, I said, Catherine, what is it that you don't get?
Sorry, there's a noise in my house. Like I'm understanding it, but like the moving back, like the numbers.
Mhm. Okay, so
Like,
let's talk about this one right here, right? Aluminum. Gonna put aluminum in orange. Here's aluminum. Okay, now remember, your goal is to be a noble gas, right? Now we want to find the easiest way to be a noble gas. You're located right here. It's okay. So then if I go this way, that's 1, 2, 3, 4, 5. If I go this way, that's 1, 2, 3. Now you always want to go the easiest way. Okay?
Okay.
So if you're going the easiest way, 1, 2, 3, 4, 5. Is 5 easier than going 3?
No.
So you always want to try to go the shortest way possible, right? So in this case, you're going to lose electrons because you're here and you're going backwards, right? So you're going from 13 to 12 to 10. So that means you're losing. That's right. It's going to be Al3 plus. 1, 2, 3. So that's how we got the Al3 plus. Okay. Now sulfur is here. Put in pink. In this case, if we go 1, 2, we'll be a noble gas, or we could lose 1, 2, 3, 4, 5, 6. Which one is going to be easier? Are you there, Catherine?
Yes, I am.
Okay, which one is going to be easier?
The 3 or
We're here. We could go 1, 2 to be like argon, or we could try to lose 1, 2, 3, 4, 5, 6.
also going to the 2.
That's right. So then we're going to try to gain 2 electrons. So that's why it becomes S2, because we're gaining 2 electrons.
Oh, okay, that makes a little bit sense.
Okay, so Edgar had a point. He says, so far, everything in chemistry seems to be about doing what's easy. That's the same thing in life, right? I mean, if you could get stuff for easy, doing as much little work as possible, aren't you going to do it? If someone is going to package something up in a bowl and hand it to you, you're going to go, well, yeah, sure, I'll take it, right? It's the same thing. It's all about energy, right? Low energy. We're lazy. Everybody's lazy. Ions, electron. I mean, they're lazy. They don't want to use any energy if they don't want to, right? What was that? Okay, so yeah, it's all about keeping a low energy, trying to do the least amount of work, you know? Okay, so let's do one more for the road, and then we'll start talking a little bit about the transitional metals. Okay, so we'll do selenium. And let's do selenium and rubidium. Okay.
Selenium is gains 2 electrons.
So what's going to be the charge?
A -2.
Okay. And rubidium?
Would be +1. Would be just plus.
Okay.
But once these elements reach their like balanced to noble gas status, that's when they can bond.
Yeah, because then they're charged.
Right.
Yep.
Okay.
So how many rubidium will I need?
I haven't even found it on the
That's
table.
right. I'll need 2. Okay, so then my
2, so it has to be over here.
It's number 37, Nate.
my ion would be Rb2SC. Now, if you notice, there was a trend on how I arranged. Do you guys notice that?
Metals first, non-metals last.
That is correct. You're always going to put the positively charged ion first, and then the negatively charged.
Wait,
Okay.
why is it RB2? I thought it's just RB plus. How did it become RB2?
What is the charge on Rb?
You mean like to become a noble gas is just 1,
Yeah.
right?
It has a +1 charge, right? But
Right.
what is the charge on selenium?
2 minus.
2 minus. How many rubidiums? How many rubidium ions will I need to balance out the selenium ion?
I get it.
Oh, 2. So okay, I got what you're saying.
Okay.
Yeah.
Okay, so in other words, it kind of just seems like you flip the numbers when you write the overall answer, right?
Cross multiply. Yes, there is a little bit of cross multiplying going on. If you think about it, you have 1 rubidium, it's a +1. The selenium is 2, right? So if you cross multiply, you need 2 rubidiums to balance out 1 selenium.
But it'll probably get more complex the farther into the table we go, right? Like it's not always going to be that clean.
Yeah, it does get a little more complex, but it's very, very simple. But for some reason, we always end up trying to make it harder than what it is.
Yeah.
Okay, but yes, Veronica, you're right about that. That is a quick way of doing it. Okay, so are you guys feeling comfortable?
A little more comfortable, yeah.
A little more
little.
comfortable?
Professor Henry,
Yes,
why did we put rubidium first again?
because it's just a trend. That's the way that we do it. You always put the metal first because
Oh,
it is the positive anion, it's positive ion, and then you always put the anion after. Cation first, anion after.
Oh, okay.
So
Thank you.
positive first, then you can talk about the negative, right? Just like you're supposed to give good news, right? I'm always supposed to tell you, like I told you guys today. Today I told you, oh, these are your top 6, right? And then I told you, you got the 13, right? So positive first, negative last. Okay, and so that's always the way it's going to be written, okay, in terms of ionic compounds. Okay, so, and we'll do one more just to kind of satisfy the question. Let's do aluminum and actually, yeah, let's do aluminum and silicon.
Would it be 3+ for aluminum?
Okay,
That would
4
be
minus for silicon.
okay. Oops. Okay. So then what is going to be my ionic?
Al1 minus silicone.
Now we want them to balance out. It has to be a neutral charge, Nate. Always have to end up to being 0 at the end.
Oh, 0.
would
Okay.
it be
Yeah.
in total 4 aluminum and then 3 silicon?
So Al4 and Si3.
An easy way of doing it is just finding out the lowest common denominator of 3 and 4.
That is correct. See, I like it when you guys say it, because when I say it, everybody looks at me like I'm crazy.
Wait, what? The lowest common denominator of 3 and 4?
Yeah, it's 12. So how many 3s do you need to make 12? You need 4 of them.
Right. How do they both become positive? I guess that's the part I'm not understanding.
What do
They
you mean
become-
by they both become positive?
Well, like
Aluminum,
that 4 minus became Si3, which is just, that's a positive, right?
no,
it's
it's
neutral.
Si3. So that's -12, right?
Because- or whatever.
-4 plus -4. What is that going to equal?
-12.
Okay, and then if I have Al3 plus, Al3 plus, and Al3 plus,
12.
okay, 12 minus 12,
0.
and that's our goal.
Yeah.
Do you see it, Nate?
I see what I understand the lowest common denominator stuff, but the final form of it, Al4Si3, is that because it took 3 Si4 minuses to reach -12?
That is correct.
And then it took 4 Al3 pluses to reach
12.
Okay.
Yep.
Okay, I understand that.
Yep.
Thanks.
So Brianna, do you see? Yep.
I don't get why the AI is 3+ though. If it's still
It's
4.
not
wait.
AI, it's Al.
Oh, AL.
Okay, Al. It's located here, right?
Yeah.
Okay, so then you have an option. If you're going to be neon, you lose 3 electrons. If you lose 3 electrons, you become 3+.
Oh, okay, I see it.
Okay,
Because you're going off neon.
that's right. Because you're going to try to be like neon. That's right.
Okay, that makes sense.
Because remember, you always want to go the shortest way possible.
And 3 is shorter than 4. Okay.
3 is shorter than 5. 1, 2, 3, 4, 5, right?
Oh, yeah.
To clarify, it's not about reaching the same noble gas, it's about reaching the nearest noble gas.
That is
Yeah,
correct.
that's what was
Yep.
getting me, I guess I should
Yes.
say.
And you always have to look at it as, so do you want to walk 3 blocks or do you want to walk 5?
3.
3, right? It's just think about it. It's always the easiest path. Okay. Does that make sense? You guys were me. Yes,
It
no,
does.
maybe?
Yeah.
Dr.
Yes.
Henry, and this is all part of ionic bonds still?
Yes, this is all
Okay.
ionic bonds still, right?
Okay.
Okay, so now these are ionic bonds. Now let me tell you a little bit more about ionic bonds. There. Can you guys see my screen? Okay, so we've talked about one other thing. So those are called monatomic ions. Each of them independently are monoatomic ion. Mono meaning one atom, ion. And so this is just basically showing you all of the ones that are isoelectronic to neon, meaning that they have the same number of electrons as neon, letting you recognize that when things have exactly the same number of electrons, they are isoelectronic. Okay. Okay, and this is just basically showing you things that are isoelectronic. Those that are in green are isoelectronic. Those that are in blue are isoelectronic to each other. Those that are in orange are isoelectronic to each other. Okay. So, can you guys write the electron configuration for the calcium ion? So what is calcium? What is the electron configuration for calcium?
It's argon 4s2.
Okay. And then for what about the ion? What ion would it form?
Positive cation.
2 plus.
2 plus. So it would be Ca
At
2 plus. And then the electron configuration for that would be
AR.
simple. Okay. Questions, concerns, Cash?
No, it makes sense.
Good, good.
Okay, so ionic compounds are going to be attracted to each other because of ionic bonds. Now, there's a couple of things that I want you guys to remember about ionic bonds or ionic compounds in general. One of those things is that most ionic compounds form solids at normal temperature, at room temperature, and normal pressure. And the reason why they do this is because of that charge, right? They're charging together, they're interacting together. They come together and they're pretty strong, okay? When there's no liquid around, okay? So they're strongly attached to each other. And so they're gonna form those solids, okay? They're also gonna form neutrally charged compounds, meaning they're gonna balance each other out. That positive has to balance out that negative, okay? They're gonna form what we call crystal lattices. So crystal lattices are gonna be like, it's going to form structures that are like positive, negative, positive, negative, positive, negative throughout the thing. And I'll show you a picture of that here in a second. So as I mentioned, they're really, really strong. And so at room temperature. And so it takes a lot of energy to sit there and get them to kind of dissociate. So you have to put a whole lot of energy to sit there and get them to break up just into their ionic compounds, or you need to put them in solution, put them in water, okay? And so, but when they're in solution, when they're in water, or if you put a lot of energy in, kind of breaking up those charges, they're able to conduct electricity. So they're pretty good conductors of electricity when water's around, or when they're in solution, water solution, because they separate into their ionic charges, or when you heat them up so much that they're separating to their ionic charges, okay? I'll show you an example of that here in a second too. So now when we think about sodium, sodium is very reactive, Okay, I'm letting you guys know that. Normally I would show you in class, but I can't show you in class. And lately I haven't been in class, so can't show you that way either. One day I'll get a piece of sodium and show you what I mean. Sodium is very, very reactive. And then when you put sodium and chlorine gas, chlorine is also very reactive. You put them together, they're going to form a very violent reaction. It's going to be very bright, colorful flames are going to be going, steam, everything. So pretty meaning that it's going to be pretty volatile, right? And that's because both of them are excited to get rid of, well, sodium is excited to get rid of an electron. Chlorine is excited to accept an electron. Since they're both really excited to do that, they're like, ooh, and so it's really volatile, right? How many of you guys eat salt?
Oh yeah, baby.
Yeah.
In just about everything, right? Salt and vinegar, potato chips,
Salt and pepper.
salt and pepper, potato chips. Okay, so just a spoonful of salt directly. Okay, so how often do you blow up because of it?
I mean, blow up with water gain, you know what I'm saying?
Not like bloating, no, not like bloating, but just, you know, boosh.
No, haven't exploded yet.
You haven't exploded yet, okay? So that says something about sodium chloride together. Each of them independently are very volatile. They cause really bad reactions, but once they're put together, they neutralize each other. Positive neutralizes that negative, right? And so we're able to sit there and eat it, right? If you ate a piece of sodium, it'll blow up in your mouth, right? You lose like half your cheek or something like that. It's pretty bad. Don't eat sodium, okay, for the record. And don't suck in chlorine gas, right? We know that that kills you, right? Because it's very volatile. It starts destroying your organs, starts interacting with, reacting with everything, right? So both of those are very, very volatile, right? But when we put them together, we get something we can put on food, right? Is that true? Or am I making it up?
It's true.
No, it's very true.
Yeah, right? And we put a lot on almost everything, right? So that it neutralizes each other, right? Making it less volatile, okay? But the reaction there would also be very reactive initially, right? So if you think about it, because you have the chlorine gas, and then it would have this really big reaction with the sodium, and that would cause it, you know, to be kind of screwed up too. So,
There is food.
you know, but afterwards they'd be okay. You know, people that come in after them.
I don't have time for that.
Where are you gonna go?
Okay, so now, so this is an example of that lattice structure that I was talking about, right? Okay, so we see the sodium atom here basically giving up its electron, right, to chlorine, to make chlorine negative. So sodium becomes positive, chlorine becomes negative. And then they alternate, positive, negative, positive, negative, positive, negative, positive, negative, right? And then so really that chlorine ion is completely negative. So it's able to interact with positives on both sides, right? And then are on all sides. And then that's the same thing with the sodium. It's able to interact with, so it basically surrounds it. But it gives this nice altering formation, forming our nice crystal lattice. Does that make sense? And so we get a nice little salt structure like this, or a little salt crystal. Okay. So this is just a couple of other ways of showing that sodium lattice. Okay. So this is the ball and stick model. This is the space filling model. And this is just showing you the internal part where a chlorine ion is surrounded by 6 sodium ions, right? And then it's just literally, you have the chlorine and you have all of the ions around it. Then you have the sodium and all the ions around it. Okay. This is basically showing us that, well, sodium chloride can actually conduct electricity when we boil it hot enough so that it actually melts. And it will melt, but it takes a lot of energy to get it to the point of melting. Okay, or if we put it in water, right? And we can also allow it to conduct electricity that way as well. Okay, are you guys with me so far?
Yes.
Okay, and are you guys kind of seeing the relevance of ionic compounds? That nice balance and what they kind of do with each other,
Yeah.
right? Okay. Okay, so next thing I want to talk about is covalent. We're doing good. Covalent bonds. Okay, so covalent bonds is when you're sharing electrons, right? So ionic bonds were about give and take. So sodium was giving up an electron, chlorine was taking an electron. You guys remember that? Yeah, no, maybe?
Yes.
Okay, so ionic bonds is about give and take. Now, covalent bonds is about sharing. So we can share electrons, right? There's two ways of sharing. How many of you guys have siblings?
I do.
I do.
Yep. Same.
Yes.
Any of you guys the oldest?
I am.
You are?
Hmm.
Okay. So I'll share a story with you guys so you guys can relate. So I'm the oldest of 3 kids, okay? So my family, were pretty poor and everything like that. My parents lived from paycheck to paycheck. So when Christmas time came, my parents would buy us one really good gift and everything else was like socks and underwears and t-shirts and stuff like that, stuff you needed for school. And usually it's you really needed it, you know. So we get one really, really good gift. So one year my parents bought me and my sisters an Atari, but it was for all of us, right? It wasn't just for me, all of us. And so they said, well, this is for you guys have to share, right? That was the rule. So my mom was really strict, share. I'm like, okay, cool, share. So the way I shared was my mom worked during the day at my sisters get out of school and everything like that. So I had about 4 hours before my mom got home. And so what I would do is I would actually play the Atari right as soon as I got home from school. And then till about 30 minutes before my mom got home, and then I'd go in the kitchen and help cook and all that crap. And then let my sisters play with it for that 30 minutes. So when my mom comes home, my mom sees my sisters playing with it, and she sees me in the kitchen. And then as soon as my mom gets home, then I take the Atari again. I said, well, it's my turn now. Okay? So overall, I get the Atari about 95% of the time. And my sister, we get it about 5% of the time. Right? Make sense?
Yeah.
My brother did that with me.
Okay.
I was the baby though.
You were the baby?
Yeah.
Yeah. So I learned a nice little system there, right? So I met my mom's requirement about sharing, right? What didn't I share?
Technically, yeah.
Technically, yeah. I met the requirement, right? So that is one form of sharing, right? And that form of sharing is called polar, right? The reason why we call it polar is because that means the electron is spending more time with one than the other. So if the Atari was the electron, it'd be spending more time with me than my sisters, right? We're sharing, right? The electron goes between both of us, but most of the time it's with me, okay? So that would form what we call a polar covalent bond. You guys get that?
Yes.
So if we have uneven sharing, it's polar covalent,
Okay.
okay? So let me type that up.
Can you give us an example of each of them?
I promise you I will.
Okay, thank you.
So polar was the first example, no?
Yep.
Okay.
So uneven sharing, polar covalent bond. Okay? Now, even sharing is called nonpolar. Covalent bond. Okay, so we have an example of polar covalent and non-polar covalent. So let me give you an example of each. So we have water, H2O. So in the case of water, this is the Lewis dot structure for water, right? So they're sharing electrons. And in this context, we're saying that the electrons that they're sharing between hydrogen and oxygen is spending more time with oxygen. The way that we're representing sharing electrons or bonding is by drawing a line between it, or we should say covalent bonding is drawing a line between it. That line represents sharing of 2 electrons. We know that hydrogen, how many electrons does hydrogen have? How many valence electrons does hydrogen have?
1.
1.
It has 1, okay? Let me clarify this. Somebody had pointed out. So this is uneven sharing of electrons. So I want you to think we're sharing. Okay, so hydrogen has 1 valence electron. Oxygen has 6 valence electrons. So here they're sharing 1 with hydrogen here, so that hydrogen is like helium, that noble gas. Here we're also sharing 1 electron with hydrogen. Again, hydrogen is like helium. And then oxygen is now like, since it has 2, 4, 6, 8, it will be just like neon. Okay. Just let me get ahead of myself. Let me get this. Okay, so here's oxygen. It needs 2 electrons to be like neon. So it needs to have 8 valence electrons around it. 1, 2, 3, 4, 5, 6, 7, 8. To be like neon, that's 2, that's 4, that's 6, that's 8. Okay, so now it has a total of 8 electrons around it. So acting like as if it's neon. Okay, so again, the way that we can become like a noble gas, we could either give, we could take, or we can share. Okay, now if you're sharing, it's going to be a covalent bond. If you're giving and taking, it's going to be an ionic bond. Okay. Okay, so this is an example of an uneven sharing. Oxygen is stronger than hydrogen in terms of electronegativity, meaning that it's going to want the electrons closer to it most of the time. So in that case, we'll put an arrow pointing in that direction, meaning that it forms a pole, right? And that's how we get polar, right? It becomes polar because it forms a pole, meaning the electron spends more time towards oxygen. Another way of us drawing this out is saying that hydrogen is what we call partially positive because the electron is spending less time over there. That's partially negative. Okay, because the electron is spending more time around the oxygen. Okay. So an example of even sharing is when we have hydrogen and hydrogen. Hydrogen bonding with hydrogen to make H2, hydrogen gas, normal state of hydrogen, right? So both of these guys are exactly the same atom. So they're going to have the same, what we call electronegativity. They're going to be pulling exactly the same. Okay, so then these guys are going to be even. Okay, and so to address, so your question is, Adam, are you there? Are you there, Adam? Or did he tap out? So Adam had asked, is uneven because it's one of the elements that has more protons attracting electrons closer, or creating an uneven direction. So uneven because the electronegativity associated with it. And so it has, it does have a little bit to do with what we call the nuclear effect, where the electrons are located at and the things that are there, but it also has something to do with just that atom space. With both of these guys, hydrogen is only one, but it's willing to sit there and share even, but it doesn't have a lot to to overcome. It just has to gain 1 electron or share 1 electron. It'd be like helium, right? Oxygen has to share 2, but oxygen has a stronger pull associated. And I'm going to show you that here when we talk about electronegativity. Okay. Okay. So you cool with you got the examples of uneven sharing and even sharing?
Yeah, I got
Okay.
a few examples in.
Okay, good.
Mr. Henry,
Yes.
I was confused. So how do we those dots on the O? Why is there only 4 again?
There's 4 left on there because how many, you guys remembered Lewis dot structures? We talked about it before you guys left.
I don't. That's what I'm struggling with.
Okay. Who said I don't? Nate?
Adam.
Adam.
No, it's Nate. I'm just playing.
Okay. So oxygen, right? The easiest way to remember the number of valence electrons is just to count the S and the P. For you guys especially, we won't worry so much about the transitional metals. We're going to ignore them right now, just temporarily. So this is an S, that's a small s, and this is a P. Make it. Got to catch myself. Small s, P. Okay, so in the second row, oxygen is in the second period. So then 1, 2, 3, 4, 5, 6. Oxygen has 6 valence electrons. Okay, hydrogen.
Wait, does it matter where you place the electrons on these charts?
For right now, it doesn't, but it will here in a second.
All right.
Okay, when we start making compounds, it'll start that. Okay, hydrogen has 1 valence electron, right? So we want to find a way to shift the electrons so that they have what we call an octet. They have 8 electrons around them, okay? In the case of oxygen. Hydrogen only needs to have 2 electrons around it because then it'll be just like helium. Hydrogen will never, ever, write this down. Hydrogen will never, ever be a center atom, okay? Did you guys get that down?
Hydrogen
It will never what?
always be in the center.
Nate, hydrogen will never be in the center. Never, ever be in the center.
Never.
It's always going to be at the end, never at the center, in the center. Okay, so we know that if you have anything that looks like this, that's wrong, right?
Okay.
It'll never look like that. Okay, so we want to make it so that hydrogen reaches its octet, which means having 2 electrons around it. So if it shares these 2 electrons between hydrogen and oxygen, that allows it to reach its octet. If these guys share these 2 electrons, these 2, they share those 2 electrons, then that means that it reaches the octet. Now, oxygen, to be like a noble gas, it needs to have 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So if I have 2 here, 4 here, 6 here, 8, is that 8 around oxygen?
Yes.
Okay, so that's our goal. We want to try to get everybody to its octet.
Do you draw
Okay.
a line between them that represents the 2 electrons?
That is exactly what we're going to do.
Okay.
So we're going to draw a line between the oxygen and the hydrogen. I'm going to put 2. These guys here, these guys are called lone pairs.
Okay.
I'll write that down.
This class will never end. I don't know. It's gonna end.
Lone pair. So these guys are lone pair electrons, okay? And they're usually grouped in pairs of 2s, if you can group them in pairs of 2s, okay? So lone pair electrons, that's why I call lone pair 2.
If you put a double bond, like 2 lines, does that represent 4 electrons?
That's right. So if there's 2 lines between it, so let me give you another example. So if we have oxygen reacting with oxygen, For it to reach its octet, because each of them have 6 valence electrons, we have to have a double bond. Okay, so then that's 2, 4, 6, 8 around this oxygen. That's 2, 4, 6, 8 around this oxygen. You see that? Nate, are you there?
Yeah, sorry, my daughter's trying to make hot chocolate and pudding right now. It's a disaster. But I stopped.
Excellent. You stopped her?
Yes.
Darn it, I wanted hot chocolate and pudding. Okay. So let's do one more for the road. And I'm going to give you a couple of hints real quick. What I always do, what I always tell you guys to do is, or what I will tell you guys to do here is, tell me the number of valence electrons I'm working. I always like to draw that out. So I have 5 that's going to be here, 5 valence electrons, 5 valence electrons. So I have a total of 10 valence electrons to work with. At the end of the day, you want to make sure that you're using all of those electrons and you're not adding any extra.
Go away, young child.
Okay, so that's 5 around here, 5 around here. So I need to change this, you know, work this so that I can actually get it so that it has 8 around each one of those. Okay, so what do I need to do? How many electrons need to be shared?
4.
How many? You said
2, right?
So you think it's just 2? So if I
3.
put 2 here, I'm gonna let's see. If I take these 2 and I put those in the middle,
You need a triple bond.
I need a triple bond. So that means I have to share how many?
6. in total.
6.
Oh, so we went up to 8, up to 16.
No, we have a total of 10 electrons to work with.
Oh, okay.
Right? So if we think about it, it's 2 here, that's 4, that's 6, that's 8. So that's 8 around this nitrogen, right? And then I have 2 here, that's 2, that's 4, that's 6, that's 8 around this nitrogen. So that satisfies the octet rule for both of them. And then we count the total of electrons, that's 2, that's 4, that's 6, that's 8, that's 10. That's 10 total electrons. So it'll look like this.
So this is a covalent bond because they're sharing these?
That's right.
Got it.
So when we draw the line, that means they're sharing.
Got you. All right.
Okay. Do you see that?
Yeah, that makes sense.
Okay. So what about, let's say, fluorine? How many valence electrons does fluorine have?
7.
It has 7.
7.
3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So how can I share so that everybody has 8 around it?
You'd have to put
7 plus 7 is 14. So I have 14 electrons to work with.
You just need a single bond and then 6 lone pairs around.
6 lone pair electrons. Okay, so like this. Okay, so that's 2, that's 4, that's 6, that's 8, that's 10, that's 12, that's 14. So that matches the number that we have. That's 2, that's 4, that's 6, that's 8 around this fluorine. That's 2, that's 4, that's 6, that's 8 around this fluorine. Obeys the octet rule. Veronica, you have that look.
So I just got confused because say when it's say when it's a triple bond or like the 2 lines, that means it's sharing 4, right? But when it's 3, it's 6.
Yep, that's right. So that's like the nitrogen here. So that's 2, that's 4, that's 6.
And when it's like 1, it's 2.
Yep,
Okay.
that's right. Yeah, so
I
a
just
single line means sharing 2 electrons. A double line means sharing 4 electrons. And a triple line means sharing 6 electrons. Okay, are you with me?
Yeah. Yeah.
Nobody wants to jump off a ship yet, right?
No, not yet.
Not yet. Good. Okay. Okay, so let's try one more before we go to lab. And then we'll pick it back up there. Okay, so let's do carbon monoxide, CO. Okay, so that's our compound. Tell me, how many valence electrons does carbon have?
4.
4.
Okay, so carbon has 4 valence electrons. Okay, and then oxygen?
6.
6.
4 plus 6 is a total of what?
10.
10.
So we have 10 electrons to work with. Okay, so how can I maneuver this so that everybody obeys the octet rule? I didn't spell it for you, did I? Oct means what?
8.
8.
8. Okay, octet.
It's a triple bond, huh?
That's right, it'll be a triple bond.
Oh, snap. It just came to me.
And then how many lone pair?
2 on each, or 1 lone pair on each. So 2
Okay.
electrons on each side.
There you go.
Ah, okay.
Oh.
2, 4, 6, 8. 2, 4, 6, 8.
That is correct.
All
And then
right.
if you count total, 2, 4, 6, 8, 10. It meets this requirement and it meets the octet rule.
All right.
Okay.
So if you were to add more elements, like in another direction, then going that direction, the shared bond would have to equal 8 as well to satisfy the octet.
That's right. So you'd have to look at both sides. Let's do one more example. See, Nate, you caused another example.
My
Let's
bad.
do carbon dioxide.
After taking that practice test yesterday for 6 hours, I have a lot of questions.
I'll leave this out. Oops.
I'm gonna do another 6-hour practice test tomorrow, and then I'm gonna go for the real.
Okay. So we have carbon dioxide. How many valence electrons does carbon have?
4.
4.
Okay. And then each oxygen has how many?
6. So would that be 12?
Okay, total of 12. 4 plus 12.
16.
So we have 16 electrons to work with. So who's going to be in the middle?
Carbon.
Carbon.
Okay, I'm sorry. I heard our.
Carbon.
Repeat that, please. Carbon. Okay, so carbon's going to be in the middle. So on the sides, we have oxygen. Okay, so how can I change this so that everybody reaches this octet?
4, 6, 8. A single bond on each side.
Are you sure?
No, I'm not
Double bond.
sure.
Because carbon.
Oh, because carbon has 4, so it needs 2.
That's
double
right,
bond?
Catherine. And Daisy, a double bond. That's right. So a double bond on each side.
And then for lone valence electrons on each.
How many? How many lone pair electrons?
8, 2, 4, 6,
4?
8.
4.
4. Okay. So 2 lone pairs, 4 lone pair electrons. Okay.
That's not-
Okay. Are you guys feeling it? Do you see it?
Yeah.
That's not as hard as it looks. For now.
For now.
For now.